Yes, sir.
Yeah, please start.
Yes, sir. Good afternoon, one and all. We welcome you all again to the third session for today. It's a great privilege for me to introduce you all to our eminent speaker for this session, Professor Sarvana Kumar. He is a professor at the Department of Engineering Design at IIT Madras. He teaches courses in the areas of functional and conceptual design, design for manufacturing and assembly, computer aided design, optimization, and rapid product development. Some of his specific research area includes CAD, design optimization, design for additive manufacturing, orthopedic biomechanics, and biomedical image processing. Over to you, sir.
Thank you. Thank you for the introduction. And so first, I would like to thank Dr. Kiran for inviting me to this FDP program. And today, I would like to talk about the 3D printing, the way most of us know, or in a more technical sense, what we call as additive manufacturing. Um, the technology, the various types of materials with which we can work, and the very many applications that can be thought of. This technology is very disruptive in nature, and thus, what could be the application is only residing in our imagination and our creativity. So, with that note, let me just share my screen. I do understand that most of the people here are from the mechanical background, and a lot of my applications and uh, technology intervention where we are talking about is in the product design and in the manufacturing industry. So I think what I will talk will be of interest to most of you. And more recently, we are working with biomedical domain. So I will also be sharing details regarding that. So let me share my screen and let me know if it is visible.
Yes, sir, your screen is visible, but not
Yeah,
yet the PPT.
yeah. I will I'll open up the PPT.
Yeah.
So, so I
Yes, sir,
hope
PPT
my
is visible. Yeah, yes, PPT is visible, sir. Yeah, and you are audible well as well.
thank you. So, as we have been informed, I am from IIT Madras, from Department of Engineering Design. We are a small group of faculty from an interdisciplinary domain of mechanical and electrical predominantly, and we work in the domain of automotive engineering, biomedical design. We have a dual degree program, MTech engineering design, uh, where the students specialize either in automotive engineering or biomedical design. So why I bring this in context is that most of the product development, as you will be aware of, requires a lot of iterations, design iterations, and optimization, proof of concept, and then you go ahead with the manufacturing. So any product development, new product development, or even a variant, let's say you want to do some small modifications, require so much of verification, validation, before it can be taken forward. So in this context, 3D printing, as we call, which was also called as rapid prototyping, and a lot of applications over several decades has been in this domain. But now this technology, whatever we are talking about, has moved from just being a 3D printing or a rapid prototyping technology to a manufacturing technology. That means today we are seeing end user parts which are coming from this technology. So in this context, our department having a design emphasis, we have been operating a rapid prototyping machine for several years, most close to a decade. The picture that you see here is the 3D printing machine from Eden object earlier, and now it is with Stratasys. The Stratasys has owned the object. So this is a multi-jet printing technology, the one that you see here. So you have this multiple jets here coming out like your inkjet printer, the paper inkjet printer. The build platform that I'm just pointing you here, it goes down and it jets the polymer, which is polymerized using a UV light. The flood light that you are seeing here, that polymerizes the part. This we have been extensively using for our product design and development activity. And more recently, we have established a center for additive manufacturing, because we have got this IOE status, if you Institute of Eminence, and we have got funding to set up some of the advanced facilities. And one of the advanced facilities is to have a metal additive manufacturing. So I will also quickly show or discuss something that we are doing in that sphere. So this is my lab. We do research in the area of 3D imaging to product design, CAE, the complete pipeline of computer-aided design to analysis to manufacturing, and all the research avenues that are there in this domain. We work on, some of these facilities that we have in the lab are listed here. This is just quickly to tell you what is the lab, and I'm coming from this place. So this talk, as I said, we will talk about additive manufacturing. We'll talk about some of the materials that we are working with. We are researching some new materials like functionally graded hydrogels. So I will talk about them, and also a lot of applications that we have done, which had both the research as well as the development content. Primarily, as you will see in this list, a lot of applications in the domain of biomedical area. Okay. So this slide describes. I am told that there has been a couple of talks on additive manufacturing. So probably you are introduced. So maybe I will quickly skip from this slide. But this is a picture that's from one of the earliest textbooks on rapid prototyping. By Chua. So this book illustrates the process where you have the computer generated 3D model to data conversion, which is basically converting into a data format understandable by the front end software of a 3D printing machine, to generating the part file, which is essentially to be built layer by layer. As you know, this process builds parts in layer by layer. So you slice and then you generate the tool parts and you then feed it to the machine. And once the part is done, you have to do some post processing, like removing the say the extra supports which are needed for the overhanging faces, as well as some post processing, finishing, and then the part is used for whatever purpose it has been made. Okay, so this picture also illustrates the same process. You have the CAD, the STL file, what traditionally used to be, and even now, but more recently we also have what is called as an additive manufacturing file format, AMF it is called as. So apart from STL, the AMF file format is also evolved, because in STL, if you would have noticed, or if you would have been told that this is basically a triangulated version of the geometry. That means it is approximated to the first order information. Several planes are used to describe a complex geometry. So if you have a curved surface, like in this case it is a sphere, it is represented by several tiny triangles, and that introduces, as you know, some errors or deviation. And it is possible with newer file formats like AMF to have what we call as the bicubic surface patch, wherein the difference, the error, not only in the absolute deviation, but also in terms of higher order information like the curvature or the normal, because in many of the applications, those higher order information or higher order continuity, what we call as, class A surfaces, wherever they are required, there the even the curvature information is important, and it is possible to have those things translated to the machine as modeled in a computer file, or as modeled in a CAD file. Okay. And we slice it, and obviously while slicing also there are errors introduced, like because you are making a 3D into a 2.5D, and thereby you introduced what we call as the staircase effect. I think I do not know whether people have talked about it. So it introduces the surface roughness where and unless you keep that layer thickness, the number of slices that you are making. So if you keep them too small, like let's say 40 microns or even less, we have this multi-jet printer that I was talking about. It slices at about 16 microns. So you can see that when you slice at such a small slices, pretty much the deviation in the profile that causes this surface roughness and deviation from the actual geometry, that could also be minimized. So some of the build parameters like layer thickness affects the accuracy and the surface finish. I think you may be also able to see here there are some serrations and deviations that are caused because of this um, slicing. So when it comes to materials, generally we have three classes of materials to start building. So we can start from powders, we can start from liquid, and we can start from solid as well. Many of the processes that use powders essentially started as SLS system, or what we call as selective laser sintering. So wherever the material needs to be fused, like we have this slice, so here I need that this region needs to be fused. So the laser will scan that region, and it will fuse the powder bed in which the powder is spread. The powder will be fused, and layer after layer, selectively the region of interest is fused. And some of the earliest machines came from EOS, which is still in one of the market leaders in this technology, and we have other companies like DTM and ZCOP. The materials could be different. It could be polymers. It could also be metal. So when we go for higher temperatures, or we use a heat source which can melt the powders, so such technologies become to be called as SLM technology, or selective laser melting. So now these technologies are also called as powder bed fusion technologies. Uh, then you have liquid based processes where photopolymer, typically polymer with the radicals which can be excited using these lasers or using UV lamp. They are used to initiate the polymerization reaction, and selectively using either a mask or again, a laser which is scanning the surface. It can selectively polymerize and you can make the parts. Many polymer based processes have been patented by companies like Cubital, one of the earlier machines. I think now they are not in the market. They had a very large build volume, and then the 3D systems they still have. They are in the market, and stereo. They call the technology as stereolithography, SLA in short. And this Eden, the object machine that I talked about, is also one amongst this class, where the material is jetted and you uh, uh, flood the UV light to cure it. And there are also other class of material forms like a solid, which could be taken either in a filament form and or in a sheet form, and they can be fused one after the other. The FDM technology, or what is now known as fused filament, modeling, or fused filament, deposition. Because FDM, I think, is a company trademark name, and thereby now, since the patent period of Stratasys was is not covering it. So you will see a lot of low-cost printing technologies coming using this fused filament modeling process. And there are a lot of machines, and probably there might be available in many colleges and in universities. This has become a very low cost technology for realizing polymer parts. So no longer this technology is very costly, at least in the polymeric domain. But in metal, yes, systems are still quite expensive, and unless justified by the niche applications or the need for the technology, it will be a little difficult to justify employing. But as technology progresses, we know the technology progression curve or the maturation curve, you will see that the technology cost comes down, and more uh, even consumer products, we will see that this AM technology will play a vital role. Right now, we see that a lot of applications are there in the aerospace, in the biomedical domain, or a few niche automotive applications have been done with AM. So these are in pictures. Again, I think I would go a little fast over here, probably presuming that some of my earlier speakers have talked about it. This is a schematic of an SLS system where you have two powder bins. From one powder, the powder is uh, spread onto the build chamber, typically a cylindrical shaped bin, and as this piston moves down, new layers are spread, and a laser selectively sinters or melts this. Many materials in the polymer domain, many grades of PLA, PP, ABS, nylon, all are available. This is a schematic of SLA process, where you have a vat of resin and the build table goes into the vat layer by layer, and laser scans polymerizing the liquid selectively. So this is one of the configurations from a commercial vendor, and a lot of photopolymers of different grades are available. Now even engineering grade plastics are available in this process. This is the fused filament process, where you have this filament spool, which is extruded, and it is taken to a glass transition temperature and deposited onto this moving table which moves in the z direction. So this is an xy table, and this is a z table, and selectively the material is deposited, and wherever supports are required, a support which is of a different plastic or a different material uh, and a nozzle is deposited. So this is one of the commercial configurations from a vendor, and again you have materials like nylon, PP, ABS, different grades of plastics. And this is a multi-jet technology that I talked about, or it's also called as the polyjet machine, where the material is jetted, again layer by layer. The head has the XY movement, and you have the Z platform moving down. So again, one of the configurations from a commercial vendor. Object, again as I said, this is purchased or taken over by Stratasys, originally from Object, and again a lot of grades of photopolymers are available. This is an LPBP technology, that is your powder bed fusion, laser powder bed fusion technology. Uh, it's very similar to SLS in terms of the mechanism of powder spread, everything. The power, the laser power is higher. And just excuse me. Sorry. Yeah. So here the wattage is higher, and thereby leading to melting. So SLM machines operate with higher energy densities, and in these techniques we also have electron beam process, or EBAM, electron beam based process is also available. So what you see here is an offering from one of the technical, one of the vendors. Is also a new startup, or I would say a new company from India, giving metal LPBF machine. And we have recently acquired one, and we have installed it in our campus. So again, since we are working with metal to prevent oxidation, the environment is purged either with nitrogen or argon. So you need to have a steady supply of these gases. Depending upon the material, like for titanium, we may not be able to use nitrogen. We may use argon, and so these are required to prevent the oxidation while the part is being built. Many materials are available here. Again, new materials are being developed. A lot of R&D happens in trying to make alloys from several of these materials that can be printed, because for each of these material we need to optimize the process parameters, because in a metal process, because of the higher temperatures, higher energy input, and the temperature gradients are very high, so this introduces a lot of built-in stresses and distortion, and one has to control it, otherwise the parts will fail. Because if the parts distort, even though we may provide supports, sometimes because of the undue stresses that are developed, these supports may break away, and the part may actually distort and come out of the build